University and the Baltic Nest Institute. But first of all, I would like to thank Sindre, Peter, and Gunnar to make this day today possible. And I really have to emphasize again that the spirit we developed during our discussion when we had the final seminars of the bonus projects Recoca, what we coordinated, and Eco Support, what Marcus coordinated, we really had a very good discussion. There were people around from the government, from the ministries, and I think it was a very good discussion. We should do this really develop this further as a tradition. So thank you very much for that. So my task, by training, I'm a biogeochemist, a marine biogeochemist. And my task today is to convey to you probably what you would say, somewhat naive view of a biogeochemist on the agricultural sector. So in my work, I worked a lot in marine areas, but I also climbed up the rivers because the Baltic Sea is an estuary and there's a lot of lateral input of nutrients from the rivers. So I work both in river catchments, but also in the marine environment. So the title of my talk is the Development Trends and Scenarios of Eutrophication of the Baltic Sea and the Role of Agriculture as a Driving Sector. This was the idea from Sindre, and I think it was a very good idea. And so the outline of my talk is first of all, I would like to show some historical trends in land use and nutrient loads to the Baltic Sea. Then a little bit about the current situation, how we see that, and nutrient accounting from agricultural sources. And we did a very detailed budget in this Recoca project on agricultural drivers. Then what does it mean for implementation of Baltic Sea management? Because as you know, the Baltic Sea Action Plan, and we were the responsible ones in our group that have modeled the scenarios and modeled the allowable inputs to the Baltic Sea. So it is we to blame for it, but we need a dialogue, of course, with people from the agricultural sector, because this in the Baltic Sea Action Plan, this dialogue didn't exist. It was simply developed by a pure, what I would say, natural scientific viewpoint. And we have, of course, to ask our question, how can we achieve the Baltic Sea Action Plan? What is possible to do? And I think this is a very good forum for that today to do that. And I will give you some scenarios. But I want to emphasize here, what I will do here is the most of this what I will present here is a large-scale budget. I'm a biogeochemist and I'm trained to calculate input and outputs of nutrients into the environment. I don't discuss agricultural practices. This I hope that I get some inputs from you guys here, because this is not what I'm trained in. But we need this knowledge, I think. So let's look to the Baltic Sea catchment. And here we see here, I think it's a very, very, very nice picture showing that the agricultural area, this is the yellow area, is of course the cultivated area is mostly in Denmark, Germany, Poland, the Baltic states. Here in Sweden we have around the Mälardalen here and south of the Vänern and of course Skåne. There's the agricultural area, but otherwise we can really say that the southern part is heavily cultivated, whereas the northern part is much less cultivated. And here we have the boreal area. But of course, most of the action which has to take place in the Baltic Sea Action Plan will be, of course, in this cultivated area. And of course, countries like Poland, where there are 40 million people, about half of the people living in the drainage basin have there, of course, an important role to play. Okay, let's go to the historical view. And this is a work has been done by Hans Estrup Andersen, and he compiled all these data, or these are data from Königsbæk and Hansen from Denmark, showing the farm gate and balance in Denmark. And I think it is a very nice view. You see really the dramatic changes that occurred in the beginning of the 50s. We had we had a balance, so the balance is the inputs, what you take on as manure and fertilizer minus the harvest, so to say. We had something like 10 kilograms of phosphorus in 1900s. This peaked in the 1980s, 90s with much higher value. No, we had 2-3 kilograms, yes, which almost 10 times as much. And now we see really how the actions we see effects that we have less phosphorus in the balance here. A similar trend for nitrogen, but we see very clearly this effect that after the 50s, fertilization and more intensive agriculture took place. So this is, let's say, a view for the former EU 15 or Western style, something like the economy. Now have a look to Poland, and here we have a view from 1870 now, and this is a book chapter I write now for the so-called Baltic Book 2. It's an initiative to write a chapter about the freshwater biogeochemistry in the Baltic Sea. And what we see here is this is the N surplus, the nitrogen surplus. Again, this is the balance between what you put on the field and what you take out as harvest. And if you have a positive sign here, this can potentially leak to the environment. Here we see we have an N surplus of 5.4 kilograms in 1800, and then due to the war, the First World War, but also political changes and difficulties and societal difficulties, we had even a negative balance. This was then positive again, but then we see the same picture after the Second World War. The nitrogen surplus really starts to increase, and here the changes then are mostly due to the political changes in 1889-90, where we see that the N balance here is still positive, but it has been reduced significantly. And this is now until 2000, and we don't know the trends right now. And I think this is also a thing what we have to discuss. What will happen with the agricultural sector in what I call maybe transitional countries, new EU countries, Baltic state, Poland, what happens? But here we see again that there was a dramatic increase. And we are still, though there's a reduction, still far above levels some 100 years ago. And this is a reconstruction from a German group here at the IGB in Berlin, and this by Horst Behren and others. They made calculations, partly measurements, but also this is observed and calculated. DIN is dissolved inorganic nitrogen loads versus the emissions. And what we see is that, of course, due to the more intensive agriculture, the nitrogen loads increase upstream the Oder. This is the Oder River, up to 60,000 tons. And then there was a decrease after the political changes. And this decrease is partly, I would say, but we can discuss about this, mostly due to the installation of sewage treatment plants, not so much about changes in the agricultural sector. Because in the Oder system, we have a water residence times of some, whatever, with groundwater, some decay, so it will take some time until we see really effects here. But I think it's a very nice reconstruction about historical trends, and we see that, of course, the Baltic Sea has been loaded with nutrients more and more after the fact. But this is a picture we see everywhere, and in the we see this. I also want to emphasize this trend. I would judge it as a moderate trend if we compare that what we see, for example, in the North Sea or in North America. All over, I would say that the agricultural sector, exceptions, of course, is Denmark, or maybe Denmark 10 years ago, but we don't have an intensive agriculture like in the Netherlands or like in Belgium. There we have concentrations of nutrients in the rivers, for example, the Rhine or the Meuse, which are 5 times as high as our rivers. So it is still a moderate, but we see the same trend in eutrophication. And of course, the agricultural sector is the most important source for nutrient inputs from diffusive sources, obviously. Okay, what have been the consequences of that? And here we see the development of anoxia. We see here we had very moderate anoxic condition. We still had a lot of oxic condition in the central deep parts of the Baltic Sea. And this is worsening until the year 2000. And also the one thing what I can say is that, and we have to discuss it later, that even though we see a decrease in nutrient loads in the last years, the effect in the Baltic Sea, this will take years, if not decades, if we really see an effect. So we still have, I think the worst situation has been recorded last year with 70,000 square kilometers of anoxic areas, which is a larger area as Denmark. And maybe 100 years ago we had anoxic areas in the order of 5,000 to 10,000 square kilometers. So these are the trends. Of course here, and this is then what happens with the algae bloom, and this work has been done by Bo Gustafsson with the Balsam model, which is developed by the Baltic Nest Institute. But this is also inconsistent with data and models from the SMHI, for example. And so this is, I think there's a consensus that this was a development. Okay, let's look at, this is a table maybe not so illustrative, but I would give you a little bit information about who are really the main contributors. And we see here that for total nitrogen load is about 19% from Sweden, 24% from Poland, 17% from Russia, and 12% from Finland. These are the major players. And it is similar, of course, with phosphorus. Phosphorus is mostly from Poland and Sweden, but we have to take into account, if we look at these loads, I said in the beginning, for example, Sweden has a lot of area which comes from, which is boreal forest. So we have a high background load of total nitrogen sources, which we cannot do so much about it. This is a relatively high concentrations of humic and fulvic substances which also contain nitrogen. So if we deal with the Baltic Sea Action Plan, we can say it's a little bit unfair to Sweden and Finland, which have a high background load, natural background load, because, as you may recall, the main logic behind the Baltic Sea Action Plan was that the countries have to reduce their loads in relation to the total share of the total inputs. And because there was no knowledge about that, how much really is the agricultural input from each country. And this could be something we could discuss. They said the total load is that what is the basis for the Baltic Sea Action Plan? And this we have to take into account. What is doable? I will come back to that later. Here, this is also one of these tables has been produced by Hans Estrup Andersson from Aarhus University here, and I think it is a very good. This is also to really to set up the stage for our discussions later on. We see here that Denmark, for example, puts on their agricultural soils about 150 kilograms. Well, this is manure and mineral fertilizer. Sweden, only half of it. Finland is in between, 110. Poland has about 100. So that, but the states in the Baltic state, Lithuania and Latvia, Russia, we have no ideas about it, and Belarus and Estonia, they are much less. But what will happen in the future? If they are not a member of the EU, there's a possibility that they will have the same loadings like maybe Denmark, like maybe Sweden, but there's a potential of an increase, of course, from these states. Okay, what we have done now, and of course I said I'm a naive marine biogeochemist or ecologist. I work together with people here to do in this Recoca project where we did a detailed budget of the agricultural sector. This is large scale. This is not on a field scale, this is really large scale. But what we have done here, we have done a so-called budget of growth, the net anthropogenic nutrient inputs into a watershed. And this works like this. We look at the fertilizer consumption, we look at agricultural and fixation by agricultural plants, we look at atmospheric and deposition as the main inputs of that. Then we look at how many people live in an area and what is the livestock, very detailed data. What do they consume? And if we say that the crops produced in an area is enough for the meats, to meet the needs of the livestock of the humans, then, or even more than the system exports. If it's not enough, then it imports of food and feed. This is calculated. And then we look at the riverine nitrogen export, and we also can deduce denitrification and losses in the system, which is very important because I will come to this later. If we take about 100 kilograms of nitrogen on an agricultural soils, maybe 20 to 30% of that reaches the Baltic Sea in average. So, and this is different. This is different in the Baltic Sea region. But this is a budget approach we have done together with Cornell University, which is one of the leading universities in the US for agricultural sciences. So the naive ecologists also work together with agricultural scientists. These are the input data, and the input data we got from partly from Joint Research Center in ISPRA, from Eurostat, FAO, and this is really a hard work to get all these data. These maps are a little bit outdated, saying that we don't have data for Russia and for the Neva catchment, but we have it now. But it is really not an easy task to get all the numbers on crop types, fertilizer, livestock on that level. And we have that data on a 10 square kilometer level. Most of you would say, what is 10 square kilometers? This is really rough. But for us, it's really fine scale. And this is also what we have to discuss because we come from different scales and cultures here. But these are all the data on livestock and when we used. And these data are also available now. For example, if you go to the NEST system of what we developed a decision support system for the Baltic Sea here at Stockholm University, we can go in and everything is online available. You can go in, and this is, for example, here the common wheat and spelt, the data you can download. You can click on a polygon and download all these data. These are the crop types for that. And then we developed a toolbox, and I would like to, I will not go in detail here, but I would like to guide you through that you understand the logic behind it, how the budget works. For example, these are the watersheds here, all these 117 watersheds. We looked at the atmospheric deposition, how large is that? And of course we see a south to north gradient. We look at agricultural end fixation, and we see here that peas and whatever, and some certain leguminoses are the most important ones. We looked at fertilizer use, detailed statistics we got from the Joint Research Center in Brussels. And we developed a toolbox, a GIS toolbox that aggregates all these data together. The next one is, of course, we have to say something about human consumption. And we look at population densities in a very, very fine grid scale and look at detailed statistics about food and feed statistics from FAO, what a common Northern European uses. We convert everything into nitrogen. Even beer and tobacco is converted into nitrogen and phosphorus. So there are detailed knowledge what every normal Northern European is consuming, that we get these data. And we have done that also for animal consumption. Here we see we have taken 5 classes for cattle. This is bovine young, male, heifers, dairy cows. So I'm a marine ecologist. I counted so much eggs in animals. I was a little bit tired about that. But it was interesting exercise for me. And here we have the same for pigs and 5 classes of that. And we use the statistics from the Swedish Agricultural University from Clayton and Steineck, the input of the output of animals in terms of nitrogen. So we convert all these flows of nitrogen into that with the detailed statistics on animals. Here the crop production, these are the data from the Joint Research Center in ISPRA, and then we use the statistical yearbooks, agricultural yearbooks, to say something on yields, to calculate what is the production, what is the need for nitrogen and phosphorus for these crops. Also, and everything is available on this. So we end up here with this NANI, net anthropogenic nutrient input in the Baltic Sea catchment, and its components. And it is not so surprising, I think. Of course, the red one is here in Denmark and northern Germany. Of course, here's the cultivated areas. We have here up to, sometimes up more than 5,000 kilograms per square kilometer. It is a large scale now. We calculate it. And then there's also, of course, areas which are losing nitrogen, here, for example, the Baltic state, because they're exporting more than importing. So these are areas which are high catch crops which export the crop types. So this is the kind of budget. And now, this is what I would say, I think we need a little bit more time to go through this figure. On the x-axis, this is the net anthropic nutrient input. So this is the entire budget, what we have done, from atmospheric deposition, from fertilizer, from nitrogen fixation, and the same for phosphorus we have done, of course. And then we look at all the agricultural statistics, livestock, human needs, and animal consumption, and make this budget. So we can say, here the loading goes from about 100 kilograms per square kilometer a year up to about 10,000, something like that. And here is the river run export to the Baltic Sea. So this is, on the y-axis, is how much of this loading ends up in the Baltic Sea. And this is not a model, this is a pure budget, this is pure observation. We only look at what comes into the system and what goes out of the system. And we see a very nice relationship here. Of course, the more you load, then the more you export to the sea. But we see here something like, if you load the system with more than 1,000 kilograms per square kilometer, the systems start to leak. So before that, there are natural processes of denaturfication they can cope with. And many of the Swedish systems are in this area. These very high ones are really cities and Helsinki, for example, or some Danish catchments, some northern German catchments. Most of this is really here. But we see also that if you put in here about 10,000 kilograms of nitrogen on a square kilometer of a watershed, you export about 30%. This is a rule of thumb. About 30% reaches the Baltic Sea in terms of nitrogen. You could say in phosphorus it's only 10%. And this makes it also so very important or very difficult to model this stuff on a large scale. What we are doing in our challenge as a biogeochemist is model 10% of phosphorus reaching the Baltic Sea in a background of 90%, which is stored in the soils, stored in groundwater. And I would like to emphasize that I don't think that we are there with hydrological biogeochemical models that we really can model the effect of whatever a certain measure in the Baltic states. I think these models we have at hand, maybe we can discuss this later, I think they're a little bit over-parameterized and they have a very high uncertainty. But this is a budget. We are only talking inputs, outputs. It's not a model. But if we do a step further, and now want to say this load, for example, here, this I've explained to you, this is everything. Atmospheric deposition, it is nitrogen fixation, it is fertilizer input, it is manure input, and of course all these input terms, they will of course have a different effect on the exports to the sea. But I think, maybe we discussed it with the people, with the model guys here on the large scale, it will be very difficult to model that, and we have to know that we have a high uncertainty. This is my message here. Okay, but what we can do here, we can look at the nutrient cascade. All these dots is a watershed in the Baltic Sea. We can look at fertilizer N application or fertilizer P application. Everything is converted to square kilometers per year, which is maybe for an agronomist a little bit strange. And then we look at the crop and production, and we have a very nice relationship. And so we can also say from the crop and production how much goes into the livestock of pigs and cattle and sheep and all these things. So we can address these drivers. And here I did a plot with fertilizer and applications. And of course, they are not causal linked, but of course here is the sum of the livestock and human excretion. So in areas where we have mostly a lot of cultivated areas. Okay, 20 minutes I've got. Okay, I have to speed up a little bit. We have also a lot of fertilizer application. Okay, the conclusion from this is that the comprehensive catchment database is available. The nutrient accounting tool allows for describe various drivers and relationships between nutrient loadings at source and river and export. Fertilizer and waste stream of equal magnitude is about that. Watersheds with high runoff, most sensitive to the Baltic Sea, because where it rains a lot, for example in the west coast in Sweden, they export 40–50% of the nitrogen loading to the Baltic Sea, whereas areas like the Eem-on on the eastern side, they export only 10–15% of it. Okay, now we have done also, we used that also for scenarios, and this we have to discuss today here. And I would like to emphasize one more time, we have a high uncertainty on that. This again is the NANI, and this is an input into our models. And now we can discuss how can decision makers forecast the impacts of different regulation concerning, e.g. land use to the environmental status of the Baltic Sea. What we have done here, we have used here the Danish model DAISY on a 10 square kilometer scale to calculate nutrient leaching. But I said before, of this nutrient leaching, not all enters the Baltic Sea. So we take into account the retention of that. Then we put that into a nest model, and then we do scenarios, for example, we can discuss. And here's a scenario of if Poland and the Baltic states would supply the same fertilizer amounts like in Denmark, in Sweden, I don't know how realistic that is. What would happen? And this would say that, of course, there's an increase in nitrogen loading to the Baltic Sea. And what is also important is here, I said before, about 30% of nitrogen, which is loaded on the sea, enters the Baltic Sea. What does it mean for the Baltic Sea Action Plan? We have to discuss that. And maybe, so the total reduction is 115,000 tons of nitrogen is agreed upon, and 20,000. But for Sweden, we said 20,000 we have to reduce. This means at source we have to reduce at least 60,000 tons. So 3 times as much. And this is what the farmers have to deal with to achieve that goal, because a lot of things is really lost on the way. To get an effect of 20,000, roughly you need 60,000 reduction. And this is something we can discuss. And this is we have done here the BSAP target and the reduction at source, because I think this matters for the agricultural scientists. And we say here in total, To reach 135,000 tons, we need 436,000 tons at source to reduce. At least 3-4 times. And for phosphorus, even more. To reduce 15,000 tons, we need 124,000 tons roughly to reduce at source. So this is the task we have to discuss. And I don't know if this is possible on which time scale, but this is something what the budget approach tells us. And we made on a very, very rough estimate. I would like to emphasize, this is nothing what can be done, or I have no idea about agricultural practices. This is a budget approach. What would this number of 60,000 tons at source, for example, Sweden, what would that correspond to? And we said that watersheds with high meat production, there we calculated reduction of wastewater streams, so we lower livestock to meet the targets. And watersheds with high crop production, we said, this is first, and this is really oversimplistic, I admit that. And we say, how much is that in fertilizer use? And if we do that, then we say that this first primarily remote, but if we want to reduce or fulfill the Baltic Sea Action Plan, this would mean that Sweden has to lower their livestock by 70%. Denmark has to lower their livestock by 50%. Germany has to lower fertilizer use by 10%. And this is the numbers of phosphorus. This is a rough budget approach. And this means that, and this brings me to the conclusions. I think I have to, no, one more slide, and then I get this conclusion. What also I would like to discuss here, and this is also possibly oversimplistic, but this is the statistics on animal protein consumption in the Baltic Sea area. We see the black curve is this from the EU 15. And we see in the 60s, 70s, we consumed 45 grams of animal protein per day. Now we have almost 70. So there's an increase in meat consumption. And this, of course, transfers to the intensification of agriculture. And here we see the dip here. These are the new EU member states, Poland, Latvia, and so on. There's a dip, of course, after political changes, but they catch up. They are almost on the same statistics. Portugal, Greece, and Spain, when they joined the EU, they increased their meat consumption with 50% within some years. And this is what we see, and this is what I see as a risk, that the Polish agriculture, which is not an intensive agriculture, may change. But this may be an oversimplistic view, but we would like to discuss with you. But if we do, like climate models say, okay, this curve goes like this, together with climate change, we might have an increase of 20 to 60% in total nitrogen loads. But this is a simplistic approach. We have to improve that, and I would like to discuss it with you. What is the perspective in the agricultural sector? And I can come to my conclusions otherwise. Okay. Key messages is that synthetic fertilizer is the main source of nutrient pollution in the Baltic Sea catchment area, and other sources such as nutrients in food and animal feed, waste stream or atmospheric deposition contribute and are sometimes dominant. Increase in fertilizer use may occur in transitional countries. Is there risk that nutrient loads to the Baltic Sea from Poland, the Baltic states, and Russia may even increase, though we have formulated the Baltic Sea Action Plan? I think there is a risk, but maybe I'm wrong. And the compliance to the Baltic Sea Action Plan will require significant changes in the agricultural sector. Agricultural practices and new techniques have to be explored. And this is not where I'm an expert in, but I think the budget really sheds some light on the role of agriculture and what can be done. And I'm really looking forward to have the discussion with you, what kind of agricultural practices and policies can be promising to achieve the Baltic Sea Action Plan, because I think it will not be an easy task. It has a political dimension that we have the Baltic Sea Action Plan, but it will be difficult to achieve. I think this is what my message is. Thank you very much.
Well, thank you, Christoph. We have time for just one or two short questions. Okay.
Have you tried to compare your results with the results of other load modeling?
So but it's also last year we compared with the Moneris model, for example. It gives similar numbers. Even if we compare it with the models from the SMHI, they're on the same ballpark. I think we had discussions during our final seminar. It's about the same. Yeah.
But the retention that you have is much higher there than what other models says.
I don't. Yeah, but this is a total budget approach. We look at all the sources, and on a watershed, this is not on an agricultural. idea.
Yeah, I know, but there is a helpful data.
Mm.
If you compare with those data, at least for Sweden, the retention that you mentioned, it's